Hello and welcome. In this lesson, we will discuss about how to use and implement the body of influence or BOI, the face of influence or FOI, local sizings, and how to create local refinement regions in Ansys Fluent meshing watertight geometry workflow. We will learn in detail what they are and how they can be used. Ready? Let's get started. In CFD simulations, it is often necessary to create regions of refined mesh to ensure an efficient capture of the complex flow physics in those regions. When using the watertight geometry workflow in Ansys Fluent meshing, there are two main ways of marking regions where we need specific mesh distribution, using BOIs and FOIs and using local refinement regions. Let's start by first understanding the BOIs and FOIs approach. BOIs or body of influence are closed three-dimensional bodies and FOIs are face of influence are open surfaces that have a specific influence on the volume mesh size inside a domain. BOIs dictate the maximum cell size of the mesh region that falls within their boundaries, while FOI dictate the maximum cell size in the vicinity of their surface. BOIs and FOIs help define what regions of the mesh should be refined, and they will not be a part of the final computational model. This is very useful since they can be added to an existing geometry at the CAD stage, removing the need to decompose the domain into multiple regions to then specify local face or body sizing. BOIs and FOIs do not need to conform to the model geometry. They can include, intersect, or just be inside the geometry or other BOIs and FOIs. Note that the BOIs and FOIs must not be connected to any other body, BOIs or FOIs, so they must be excluded from shared topology. Let's now try to understand this with the help of an example. In the import geometry task, locate and select the geometry file example BOI-FOI for this exercise. Activate the clipping planes and reposition the plane in order to show the internal geometries. Here we have two fluid regions containing four objects. The sphere and the short tube are solid bodies, while the cylinder and the open surface are the BOI and the FOI respectively. In the Add Local Sizing task, select Yes to add local sizing. In the panel under Size Control Type, select Body Size. Set 2 mm for the target mesh size and select solid 1 among the labels. Click on Add Local Sizing to apply it. Next, select Body of Influence as control type and enter 1 mm for the target mesh size. Select the BOI label to apply the controls to the BOI we created and again press Add Local Sizing. As soon as you press the button, the BOI disappears from the displayed geometry. This is because Fluent meshing recognized that the body is not a part of the geometry but just an entity that drives the local mesh refinement. The next step is to set a face sizing on the pipe-shaped body on the right and a FOI size for the cylindrical surface. Set the new control type to face size and set 2 mm for the mesh size. Then select the solid 2 surface label and apply the local sizing. Last, set the face of influence sizing with a mesh size of 1 mm and apply it to the FOI using the proper label. Again, as seen for the BOI, the face of influence disappears as Fluent meshing recognized it as not part of the geometry. Now, all the local sizings are set and we can continue with the rest of the workflow. Go to the Generate Surface Mesh task, set the minimum mesh size to 1 mm and leave all other settings to default. Then click Generate Surface Mesh. In Describe Geometry task, change the geometry type to the geometry consists of both fluid and solid regions and or void and select Yes to change all fluid boundary type from wall to internal and then update the task. You can keep the default settings and values for the rest of the tasks and just click update to each one of them. In the Generate the Volume Mesh task, select polyhex core for the fill width option and click the generate the volume mesh button. Here is the generated volume mesh. As you can see, the exact position of the BOI and FOI objects cannot be determined precisely, while the two solid bodies where we applied body and face sizing are very distinct. This is because the latter ones define specific regions of the domain, whereas the BOI and FOI influence only the mesh sizing in the regions they were defined in. You can notice that both BOI and body sizing prescribe a mesh sizing at the volume level inside a specified volumetric region. However, the BOI does not have to be a unique cell zone of the domain. Also, you can see that the fine mesh size of the BOI locally overwrote the body sizing. FOI and face sizing influence the volume mesh indirectly in areas nearby the surface locations. However, the FOI does not have to be a real boundary of the geometry. BOI and FOI gives flexibility to control the volume mesh refinement for localized regions such as wakes or shear layers, but they cannot be used to specify zones or boundaries for the simulation. Even boundary layer meshes cannot be applied to them, so be mindful while using them. An alternate way of creating refined mesh regions without the need of creating separate geometrical bodies at the CAD stage is by using the Create Local Refinement Regions task of the watertight geometry workflow. To know more about this task, let's import a new concept car geometry. In this geometry, we have a concept car placed inside an enclosure which acts as the fluid domain and can be used for performing external aerodynamic type analysis. For this demo, we will not be using any local sizing, so leave the option to no in the Add Local Sizing task and hit Update. To include the Create Local Refinement Regions task, right-click on the Add Local Sizing task to access its task-specific context menu, and from the Insert New Task menu, select Create Local Refinement Regions. This new task is placed immediately after the Add Local Sizing task in the workflow. In this task, under the Type drop-down menu, you can choose between two options, Box and Offset Surface. Let's start with the Box Refinement type. The Box Refinement type, as the name suggests, lets the user construct a box around the selected geometry to define specific mesh sizes. There are two ways in which the box can be defined, and these options can be found in the Coordinate Specification Method drop-down menu. The default method is the ratio relative to geometry size. When using this method, the user must provide the limits to which the box extends to by specifying the minimum and maximum values as a ratio relative to the length of the selected geometry in that specific direction. Here is an illustration of how the ratios are used to create the box around the selected geometry. As you can see, if the length of the body is L in the X direction, and if the min and max ratios are 0.1 and 0.2 respectively, the minimum extent of the box would be 0.1 multiplied by L, and the maximum extent would be 0.2 multiplied by L from the surface of the selected geometry. Coming back to our demo, let's select car surface zone. Immediately, you will see a graphical representation of the box placed around the selected geometry in the graphics window. This box is also overlaid with smaller size boxes which represent the size of mesh that will be created inside the box, which is controlled by the mesh size input. The second method to create the box is by providing the absolute coordinates of the minimum and maximum locations by selecting the directly specified coordinates option from the Coordinate Specification Method drop-down menu. These are global coordinates with respect to the origin of the model defined during the CAD creation. For our demo, we will select the ratio relative to geometry size option with a mesh size of 80 and rest of the options at their default settings. Follow the steps as shown here and create the volume mesh. Here is the generated volume mesh, and you can clearly see the influence of the box local refinement region on the mesh size in the region enclosed by the box. Now Let's see other type of local refinement region, which is offset surface. When offset surface is selected, we need to first define the mesh size and the geometry from the object selection panel. Note that the selected object must be a closed entity. We will discuss the mesh size parameter a bit later. There are a few additional inputs that user needs to provide in the offset parameters section. First, the flow direction needs to be picked. This is to ensure that the wake levels are grown in the correct direction. Next, a defeature size needs to be provided, which basically is the size of the facets used to create the offset surface from the selected geometry. A smaller size means the offset shape will more closely resemble the shape of the selected geometry. Usually, a coarse representation is sufficient. Two types of refinement regions can be created using the offset surface type: boundary layer levels and wake levels. The boundary layer levels are surfaces created by scaling the surface of the selected geometry equally in all directions with respect to the center of the selected geometry. The boundary layer height defines the offset distance of the farthest boundary layer level from the geometry. The boundary layer levels parameter defines the number of regions that are created within this height. If more than one level is specified, each level will have equal width but a different mesh size. Wake levels are like the boundary layer levels except that they are not equally scaled in all directions. These are primarily used to create BOIs with extended domain in the downstream of the wake region of the selected geometry. Here is an illustration of how scaling works for the wake levels. First, the length of the body from its center to the outermost boundary layer level is calculated in both upstream and downstream directions. Subsequently, the offset distance from each of the wake levels is calculated using these length values, the wake growth factor and cross wake growth factor. The wake growth factor and the cross wake growth factor control the offset in downstream and cross wake directions respectively using the formulae shown here. For both the boundary layer levels and the wake levels, the mesh size parameter is used to define the sizing of each level, which increases by a factor of 2 between successive levels. For example, if we define one boundary layer level and one wake level for our geometry with a mesh size of 20, the boundary layer level will be meshed with a size of 40 and wake level with a size of 80. Follow the steps as shown and create the volume mesh. For brevity, we will skim through the steps. Here is the generated volume mesh using the offset surface method. You can clearly see the influence of the two local refinement regions. Let's summarize what we learned in this lesson. We learned about how to use BOI and FOI local size controls for refining the mesh in specific regions of interest in the model. Then, we understood how to use box type local refinement region. Finally, we learned about the offset surface type create local refinement regions task of the Ansys Fluent meshing automated geometry workflow. With that, let's wrap up this lesson.